Okay, we're going to wrap up 9.3 today with a couple of special cases. So 9.3, day 3. The first one we're going to do, we've done before, or you've done before. We're going to do that natural log of x with integration by parts. Then we're going to put it on the blue sheet and just use that rule because it will keep coming up. So first, you know you have to let the u equal ln of x, because at this point we don't know how to do the antiderivative of ln. So we're going to let u equal ln of x. Ln of x. And then the v be the 1 dx. So we'll do derivative here, that gives us 1 over x. And then here we get to x when we do antiderivative. So we will multiply and then subtract the integral. So it will be x times ln of x minus the integral of x times 1 over x. The x's are going to cancel out. We're left with 1 dx. Antiderivative of this is 1. So our final is that the antiderivative of ln of x, or the integral of ln of x, is x ln of x minus x plus c. You can go ahead and add that to your blue sheet down in your integration rules. I've already done it. The integral of ln of x dx equals, and we're just going to be able to use this now instead of doing the by parts every time, because it's going to come out the same. So add that to your blue sheet. So we will use that on our next example. Example 2, we are going to integrate log base 6 of x dx. First thing we're going to do is use our change of base to switch this into a natural log. And if you remember on your blue sheet, change of base of log base anything of x, you can change the base. We're going to go with natural logs because we know how to integrate that now. Natural log of x over the natural log of the base. So we're going to rewrite this into an ln. So we'll have ln of x divided by ln, the base is 6. And remember, the ln of 6 is just a number. So I want you to see it as 1 over ln of x. I did a 1 times there. 1 over ln of x, I'll grab a color, is a multiplier. Excuse me, 1 over ln of 6 is a multiplier. So I'm just going to pull that right out in front so it doesn't bother you anymore. So 1 over ln of 6 is a multiplier. And then I have the integral of ln of x left. So using my shortcut now, I keep my multiplier, and then I multiply it by the antiderivative of ln of x is just x ln of x minus x plus c. X ln of x minus x plus c. And that's it. Done. So you're going to be using your change of base. The next one I want to do is sine squared and cosine squared. Now the book in this section made us, well, they did it the long way, using the integration by parts, but when you take Calc 2 in college, they are not going to have you do it by integration by parts. They're going to have you use trig properties. So we're going to stick that in here. Say I want to integrate, where's my problem I want? Right here. Cosine squared, any cosine squared. I'll just go cosine squared of x dx. So we're not going to use integration by parts here. We're going to use trig properties. And the trig properties I want you to look at are the double argument. So if you look at the double argument, we're going to rewrite cosine squared as, I'm going to distribute the 1/2 in right now. So 1/2 plus 1/2 cosine, double the angle. So, rewriting this, I will have the integral of 1/2 plus 1/2 cosine, double that angle. Now this is something that we can do the antiderivative of each term separately. So the antiderivative of 1/2 is 1/2 x. Now we'll do the antiderivative here, but remember we've got an angle. We have to have the derivative of the angle next to the dx. So derivative here is 2, so I need a 2. So I need another 1/2, but just on this one term. So I'll have 1/4, and then cosine's antiderivative is sine, 2x. And we could leave it, well, no, we can't leave it there. We have to finish in the same format as this one. So what we're going to do, because I've got a double angle and I need to go back and finish in the angle that I have, the single angle. So we're going to use that double argument property again, well, a different one. It'll be the first one, but it's in the double argument section, where if I have the sine of twice an angle, I can make that equal 2, so the 2 comes out in front, times sine of half of this angle, which is x, times cosine of half of the angle. So I've got, right, let's see if I can get these both on here. Yeah, so I'm going to follow this. I've got 1/4 sine 2x. So I'm going to keep this 1/2 x. I keep the 1/4. Now my 2 that I have here comes to the front. So times 2. And then my sine, my angle gets cut in half. So instead of 2x, I'm down to x. And then times cosine x plus c. So we used the double argument twice, once to get it into a form that we can integrate, and then once to get it back to the form that it started in terms of x. This is much, much quicker than doing integration by parts, which I'm not going to take you through. Now I want to do one that's a little bit trickier, and I'll switch it to a sine. Say I want to integrate sine squared of, oh, let's go 3x. So first of all, anytime you see a sine squared or a cosine squared, we want to use this property right here to break it apart into, get rid of the squared. So, we're using the double argument. And I'm using the one right down here, switching out sine squared. Get them both on here. So I see the one, I'm going to distribute the 1/2. So I will have 1/2 minus 1/2 cosine, and I have to double the angle. So I have a 3x, so I'm going to have 6x. And I'll bring it back into 3x at the end. So now let's just do the two terms separately. So again, antiderivative of a half is 1/2 x. Here, oh, that was supposed, yeah, that's cosine. I have to have the derivative of the angle, which is a 6, so I need a 1/6. So I'll have minus 1/12. Cosine's antiderivative is sine. Keep the 6x. Okay, now I'm in terms of 6x, I've got to use that to take it back to 3x. So what you want to do here, this one's a little trickier, you want to write this as double 2 times some angle. So what I want you to see 6x as is 2 times 3x. It has to be written as a double angle. So 2 times something to give you this. Double parentheses. So now we use that double argument again to go backwards. So here's my sine twice an angle. So for me, I've got twice my angle is 3x. So I will keep the 1/2 x. Remember the 2 poles out in front. So I will have 2 over 12, which is 1/6. So that's the 2 that I pulled out in front is right here. And then the sine of half the angle, which is 3x, times cosine of 3x. And then a plus c. So you're going to be using the double angle twice anytime you have sine squared and cosine squared. And then I have one left, and it's a doozy. We're going to go back to chapter 8 and do a volume. So, number 4. Can you find the volume generated by revolving the region in quadrant 1 bounded by y equals x squared e to the 0.4x and x equals 2 around the x-axis. Okay, so if you graph this, this is parabola-like in the first quadrant. X equals 2 is a vertical line. So we're in quadrant 1, we're taking this region here and going around the y-axis. We have options to go vertical or horizontal. I'm going to stick with vertical. That way I don't have to switch my equations around. And if you remember, it hasn't been that long, when it's perpendicular to the axis, it's either cylinder or washer, and because your rectangle touches your axis, this is cylinder. So we are going to do cylinder formula, which volume is pi r squared h. So our radius is the height of the rectangle, so our radius is given by the curve x squared e to the 0.4x, and our height is the dx, and our boundaries will be in x values, so 0 to 2. So we're ready. So the volume can be found by integrating from 0 to 2 pi times our equation x squared e to the 0.4x. That whole thing has to get squared. The radius is squared, and then dx. So I'm going to distribute that in. Rule is power raised to a power is multiply. That'll become x to the 4th. That'll become e to the 0.8x dx. And we will go integration by parts because you've got the product of x terms here. So we will let u equal the x part because I know that'll get down to 0. And this will be the dv part. So u is going to start out as pi x to the 4th. dv is the e to the 0.8x. So now I'll go derivative here because I know this is going to come down to 0. So 4 pi x cubed. Come down again. 12 pi x squared. 24 pi x. 24 pi. And then 0. I double check that. No one here to check my work. 4, 12, 24, 1. Okay, I think I'm good there. Okay, antiderivative here. Remember, you need the derivative of this next to the dx. So I need a 0.8 over here. So I need a 1 over 0.8. So the antiderivative will be 1 over 0.8 e to the 0.8x. And I've got to do that 1, 2, 3, 4 more times. So again, I need a 0.8. So I'll need another 1 over 0.8. I'm going to write that as 1 over 0.8 squared because of the extra one I need from this one. Now to come down again, I need another 0.8, a 1 over 0.8. So this will be 1 over 0.8 cubed. And then one more time, 1 over 0.8 to the 4th. And then one last time, 1 over 0.8 to the 5th. So, this will be 1, 2, 3, 4, 5. That's going to be a 0. So we got plus, minus, plus, minus, plus. So this gets to be a lot of writing. So we've got pi x to the 4th. How do I want that? Pi over 0.8 x to the 4th e to the 0.8x minus 4 over 0.8 squared pi x cubed e to the 0.8x and plus 12 pi over 0.8 cubed x squared e to the 0.8x minus 24 pi over 0.8 to the 4th x e to the 0.8x. And the last one is plus 24 pi over 0.8 to the 5th e to the 0.8x. All of that evaluated from 0 to 2. Now, I'm not going to take the time to type that all in the calculator and plug in the 0 and the 2. I'll save that for you for homework. No, you don't have to do that, but you get the process at this point. So we're not going to leave those Chapter 8 formulas behind just yet. And that is it.